Ready? Okay, so actually, Alexei has covered some of the introductory part of my talk. The isomorphism problem, if you talk about the isomorphism problem in a class of groups, so you want to compare any two groups from a given class, then there are not so many results relevant. Probably the most well-known and sort of the most comprehensive result is a solution of the isomorphism problem for finitely generated nilpotent groups. Then another class that was covered is the class of hyperbolic groups. So first, Sella solved the problem, the isomorphism problem for torsion-free hyperbolic groups, and then the Manish Girardel for the general case. I would say that their solution is not digitizable in the sense that it cannot be implemented in any known computer language. But it's an algorithm in the sense that at every step you know what to do, like in everyday's life. You know what to do, but you can't digitize that. And then, so that's not a complete solution. That's in the same paper that Ilya mentioned in his talk as an application of the theorem that Ilya mentioned. There was a solution of the isomorphism problem for generic one-related groups. So the solution says that given a relator, you can figure out whether this relator belongs to a generic class of words in a free group. And if it does, and if the other relator in the other group also does, then you can figure out whether the one-related groups are isomorphic. So this is not like, of course, not a complete solution of the isomorphism problem for one-related groups, but given two random relators, two random one-related groups, you can solve the isomorphism problem. So that's more or less all that is known about the isomorphism problem in a class of groups. And like I said, basically the only completely satisfactory solution is this for the class of nilpotent groups. So then, yeah, what's next? Like Alexei mentioned, of course, this problem for the in the class of finitely presented metabillion groups. Why? Because most algorithmic problems for finitely presented metabillion groups have solutions by now, and an excellent summary in that direction is in this paper. So any algorithmic problem about metabillion groups that you can think of, and even those that you cannot think of, they are solved, except for the isomorphism problem. Most of them positively, but some of them negatively. Yeah, but for example, equations in even in free metabillion groups, equations are not. Now, not in every class of groups it makes even sense to ask about the solution of an isomorphism problem. It only makes sense to ask for classes of groups where the work problem is solvable. So if you depart from the class of metabillion groups a little bit further in the direction of solvable groups of higher derived length, there's an abstraction that comes from this classical paper by Olga, that there are finitely presented solvable groups of derived length 3 already, and of course, in already higher derived length, where the work problem is not solved. So the situation is not very sort of promising. And that's why we turn our attention to the isomorphism problem. The isomorphism to a particular group rather than trying to solve the isomorphism problem in a array of two groups in a given class of groups. Let's just fix a group and ask if another given group is isomorphic to this fixed group. Now, if you're sort of not imposing any restrictions on this fixed group and on another given group, then the problem is not solvable. That follows from a classical result of Adyan. So you need to say something special about your fixed group. So the inspiration here was the paper that Alex also mentioned, the paper by Groves and Miller on recognizing pre-Matabelian groups. So the main theorem says that given trying to present a Matabelian group, you can decide whether or not it is a pre-Matabelian rank. So we can generalize this in the following direction. Consider groups that are free in a variety. So, never mind what this means. The important property of a group that is free in a variety that we're going to use is that any homomorphism, any map from the generators of this group to generators of another group, and this in the same variety extends to a homomorphism. So that this important property of a map being a homomorphism here will come for free after you impose this condition on your group. Okay, so another condition that we impose here, well, two conditions actually. One is that the word problem is solvable in this relatively free group, but that's unavoidable. And yet another condition is that this relatively free group is Hopfian. So it is not isomorphic to any of its proper vector groups. It was an open problem for a while whether or not there are non-Hopfian relatively free groups. And the examples were constructed by Ivanov and Storozhev. But of course, their examples are rather complicated, and in most like reasonable groups studied by the mankind, the free groups and varieties are Hopfian. In particular, this is the case for solvable groups, even we call them important groups. Those are even really defined, and therefore Hopfian. So we can, what is interesting about this theorem is that we do not impose any restrictions on the other group, on the group G, from the same variety. Well, it's not completely true. We do impose a condition that this group has the same number of generators. That's actually a very restrictive condition in the context of the isomorphism problem. But on the positive side, we do not require that the group G has solvable word problem.
What would this say if you took the variety consisting of all groups?
We'll get to that.
What?
We'll get to that, yes. So problem, right. So in particular, what did you ask? You probably asked because that implies that you can decide if a given group is isomorphic to a free group.
If it has another.
Yeah, that's the previous. Right. So yeah. So you picked it. The problem is that it only holds for groups with the same number of generators, which makes the corollary for free groups trivial. Of course, if you have a free group of n generators and another group of n generators, then you immediately see whether it is free or not. Whether there are generators or not, it's true. Okay, so what can we do nevertheless with a free group? So we can decide whether a given group is a finitely represented group is isomorphic to a free group, even if the number of generators is greater than n. But then we do have to impose the condition on the group G to have solvable work problem. And that is no longer trivial. So for that result, it's a cheap trick. It's the same trick as was used by Philip Hall in solving the word problem for residually finite groups. So you run two algorithms in parallel. One does one thing, the other does another thing. And so sooner or later, one of them will stop and do the rest. So the same kind of cheat trick is used here. So we do have this homomorphism for free. So we have n generators of the group Rn of the free group in the variety. We have n generators in the group G. So we map n generators from Rn to G. This extends to a homomorphism, even to an onto homomorphism. So then we run one algorithm who is looking for the kernel. If there is a kernel, then there is no isomorphism because of the Hopfian property. And then the other algorithm, the positive algorithm, just runs over all possible maps in the opposite direction and see that the combination or this solution. So the positive side is always there. Right. Here, yeah, because of the number of generators having greater than and the rank of the free group, this cheap trick is not enough. So here you have to use results on solid equations because you need to figure out whether your map is a homomorphism, and that amounts to solid equations. So here you make a map in the opposite direction from the group G to the given free group, and to check if it is a homomorphism or not, you have to solve associational equations. And not only that, you need a description of solutions, and if there's a tuple of solutions of rank n. So then it will be an isomorphism to a subgroup of rank n of a free group. And since every subgroup of a free group is free, then we are done. So this ingredient is needed because unlike in the situation with the relatively free groups, your homomorphism is now in the opposite, your map is in the opposite direction, not from the big group on your group G. It's in the opposite direction. And there's no guarantee that M is going to be a homomorphism. So that's the problem.
How do you check that it's not isomorphic?
You're looking for the kernel. So after you got these.
From G to F.
Yeah. Yeah. So now that G has a solvable word problem, you can do that. So you can look for words that are not representing the identity in G and map them and see if they are in the kernel.
Maybe there is another homomorphism which will be monic.
But you have a description of all of them, basically. From as well. but they are equivalent under isomorphic. They are isomorphic, right? Two groups of the same rank are isomorphic. So all we care about is rank. So that's the advantage of a free group.
Because it might be some solution far away, different ranks suddenly.
Yeah. Yeah, but you have a description of all of that.
I didn't really understand why you need solutions of equations here at all. I mean, G is finally presented. So if you have a map from the free group.
No, you need a map from G to the free group.
Yeah, okay. Yeah, from G to the free group, you just need to decide whether or not.
It's a homomorphic.
Yeah, so you look at the defining relations of G and you look at the images and you have to check whether they're equal to 1, right? In the free group. I mean, I don't understand why you need
It's
equation.
surjectivity, isn't it? It's surjective, we have to.
So you build one kind
Oh.
of word diagrams, right? You solve the system of equations which are the relations of the group G. Right? So you build one kind of word diagrams and look what is at the bottom. Right?
Also, there is the specialization there, the variable which
Yes, so
is
it's
going to control.
specializations of theory. No, but it's like, okay, so basically. And so, like, I mean, if you found the free group of rank n in the bottom, then what? Yeah.
Well, there are only so many possible ranks, right? Because the group G has a certain rank, so it can be isomorphic to a free group of a higher rank. So you're just checking isomorphism to free groups of rank less than or equal to m, right?
So you pick a solution, you got a map, right? Suppose the rank of the image is whatever you want, n. But you need to check that there are no kernels there.
Yeah, and then you run these two algorithms in parallel. One is looking for a kernel, the other one is looking for isomorphism.
You're looking for the kernel of infinite many things you don't know, maybe build somewhere.
Yeah, there are infinitely many things, yes, but sooner or later, one of the two algorithms will stop. As long as they have like a recursive description, so you can.
Okay, sorry, you'll explain later.
Right. So anyway, how in what direction can you generalize this? So apparently you need to be able to solve systems of equations in a group in order to sort of do this, to start this whole machinery, to look for homomorphism, find possible solution of system of equations or possible candidates, candidate subgroups in your group. But notice that what this sort of method gives us is an isomorphic of the group G to a subgroup of a given free group. Right? It's good that subgroups of a free group are free. So if your group G is isomorphic to a subgroup of a free group, then it is isomorphic to a free group. But that is certainly a very special property, right? Special for free groups. So how can you hope to get something similar in other groups other than free groups? But what you can do is to find out whether or not G can be embedded in your group. Right? So it's whether or not it is isomorphic to a subgroup of your group. And of course, in your group has to have all these properties, equations have to be solvable, and not just solvable, but solutions should have nice descriptions. Subgroups generated by solutions should be finally presented, and so on. And also the group has to be Hopfian, and the work problem has to be solvable. So the only class of groups, as far as I know, that satisfies all these conditions is the class of limit groups. So what this theorem says is that given a group G, and the only thing you know about this group G is that the word problem is solvable, and G is finally presented, and the word problem is solvable. So you have an algorithm for solving the word problem in G, and then it is algorithmically possible to find out whether G can be embedded in a given limit group. So that's what you can do. Now, to replace, like, for example, limit groups here, a limit group in this context with a hyperbolic group, for example, is not going to be possible because in hyperbolic groups, even though equations are solvable, but they don't have these additional properties, you cannot, like, for example, not every finitely generated subgroup of a hyperbolic group is finally presented. Also, yeah, I guess I'll just already this is breaks down this whole machinery. Although on the positive side, hyperbolic groups are Hopfian, and not only that, but every subgroup of a hyperbolic group is Hopfian. But unfortunately, solutions of equations cannot be sort of described as nicely as in free groups or middle groups. Yeah, so sort of a high level proof here. Yeah, so first we map generators of the given group G into the group H, and if we want it to be a homomorphism, then these system of equations has to have solutions, and yeah, so the key property here is that M tuples of solutions of this system generate only finitely many subgroups up to isomorphism. So we can ask for isomorphism to each of these finitely many subgroups Hi. And if our group G is not isomorphic to any of them, then it is not embeddable in the group H. And the way we check the isomorphism to Hi is, again, this. Yeah, we also need a presentation. We also need a finite presentation of each of Hi that comes from this paper. Yeah, we need this presentation because we will only need we will also need the homomorphism in the opposite direction. That would after being composed with original homomorphism that would give us the identity map. And in order to do that, we need the finitely many defining relations in the groups Hi. Okay, so after that, after we get these finite presentations of the groups, subgroups Hi, we do this usual trick. We run k algorithms by the number of subgroups Hi. So for each Hi, we run its own algorithm, Ci, and each algorithm Ci consists of two algorithms running in parallel. AI detects non-isomorphism by looking for a non-trivial element in the kernel.
So isomorphism is solvable for unit groups as soon as you have 2 unit groups.
Yes, but G is not a limit group. It is not given at least. And the other one will detect isomorphism. But yeah, like you said, to detect isomorphism, you can also use Titze transformations as long as you have finite presentations of both groups. Okay, that's it.
You ask questions about
The first one, or about the limit groups, or about the free groups.
okay. Rank is greater than
Yeah.
So how do you determine that G is not isomorphic to a free group of rank 10 here?
So I have a description of all homomorphisms from G to the free group.
Oh,
And
okay.
I'm looking for the kernel.
Yeah, but I mean, if you find one where there is a kernel, I mean, so I'm confused about the logic. You know, so you're enumerating all homomorphisms, and you're also enumerating all candidates for the inverse homomorphism, right?
No, for the kernel, I don't enumerate inverse homomorphisms. So I only look for a kernel of a homomorphism from G to F, to free group.
But let's say you found somehow homomorphism like that, which do you know? You're not assuming that G is Hopfian here. So I'm just confused about the logic. How do you certify that G is not isomorphic with the free group of rank M? Let's say you found a homomorphism where there is a non-trivial kernel. So what does it tell you?
That tells me that so if there is a non-trivial kernel in the homomorphism onto a free group of rank M, it tells me that G cannot be isomorphic to a free group of rank M.
Oh, yeah, that is correct. Yes. Yeah. Right. So here you're using typicity of the free group of rank M, right? Yeah.
So you have suppose you have a homomorphism, like okay, so from G of rank 5
So using the free group or something.
to free group of rank 4, right? So you have a homomorphism.
Mhm.
And then you're looking for the kernel of what of this homomorphism. There are infinitely many homomorphisms. Like I mean, this homomorphism can be like shifted by automorphism.
Yeah, but by
This
automorphism.
homomorphism is actually an epimorphism.
Yeah.
So you're enumerating epimorphisms. Yeah. It's okay. That's the logic. I haven't understood how you actually enumerate, how you make sure that the sin is an epimorphism as opposed to just homomorphism.
Yeah.
Is that why you need equations?
To decide if this is a homomorphism. Yeah, if this is a homomorphism.
But I mean, how do you check that it's onto?
It's onto something. It's onto a free group, onto a subgroup of free group.
Yeah, but you just compute the rank of that image and check if it's equal to n, you keep it. If it's not equal to n, you throw it out. Okay.
Well, still, you have to process. One checks whether there is an isomorphism, say it's a transformation. It works and works and works. If we found it done, but it works and it's not. You see that it doesn't stop. On the other hand, you enumerate homomorphisms from G into F and looking, say, P1, P2, and so on. Check the kernel. and suddenly you found, yeah, F1, P1, there is a kernel, so you cross it out, but.
No, you don't cross it out. No, I mean, you first check the rank of the image. So if the rank of the image is equal to m, and then the homomorphism at the kernel, non-trivial kernel, then you just stop and you declare that the group G is not isomorphic to
The free group of rank M.
You don't do anything else. Yeah, you just declare it.
Yeah, it speaks 10.
Yeah, I must admit I'm still missing why you need equations here, but
No, equations, you need to enumerate the homomorphism.
you don't. I mean, G is a free group.
No, G is not free.
Sorry, G is a finely presented group.
Yeah.
Why do you need equations? I mean, you just
You take relations and make it a, relations, make the equations solve it. Every solution gives a homomorphism
no. I mean,
from G to F.
that's not what you're supposed to do. So you have the generators of G. You just send them to some words in the free group.
But G is not free.
It doesn't matter. I mean, and then you check whether the images of the generators they satisfy the defining relations
Yeah,
of
that's
G.
also another way, yeah.
I mean, in order to do that, you do not need equations. You just need the word problem in the target group.
No, but you you don't know where to map your generators of
But you
G.
map all
You
tuples,
enumerate all tuples, and you check them one by one. You know, so whether or not they, you know, these tuples they give you something.
And given a
you know,
couple knows the rank.
You worry about the rank next. So you first check whether it defines the homomorphism, and then if it defines homomorphism, then you
Then you
consider.
check the kernel.
Yeah, then you start enumerating the kernel, you worry about the rank, you do all those things. But I don't see where you need equations here. I don't.
No, you don't, you do it this way.
So you have already pretty many procedures, so you might do that.
It's like in, make it into S10. You map wherever you want, check the relations hold or not, and you got a homomorphism.
This requires a more careful thought because you will also need to detect isomorphism. So if you have to check that you don't go into some kind of
I mean,
infinite loop.
my feeling is for isomorphisms, so you try to find sort of the map that goes the other way, and you check them together, and you see whether or not they, you know, I mean,
Yeah, but when do you stop? So if you
with isomorphism, you stop if the compositions in both directions give you identity maps.
yeah, that's on the positive side, but
On the negative side, you explain what you do. You know, so.
yeah, but that's for homomorphism. So if you have like infinitely many, if you just go over all tuples,
You will either find an isomorphism or you will find the situation that you described, I think, right? You know, so if the group, I mean, the group really can be generated by, let me see, well, I'm missing something here. So I guess maybe one needs to explain why one or the other will terminate, right?
yeah, no, like I said, this requires more thought. But if you are right, then we also don't need the equations in limit groups, right? And in this case, yeah, but yeah, we'll have to think about it. Okay, anyway.
No, it's not the same. But involves n plus k generators
Like a fractal, that's.
and elevators.
Mhm.
So, and because this is k generators, then they are free generators. In particular, m generators and elevators. Right?
Yeah.
There is algorithm to determine whether given n generators.
Algorithmic fractal, yeah. That I think was done by someone. That's
N
called,
minus n.
yeah, I understand. That's called algorithmic
You can find-
frequency.
yeah.
If you do,
Efficient.
yeah, yeah. Okay. If there are no more questions, and that's.